Now we're going to bump this up and do the whole process, just like we did with the direct questions. We worked with z-scores and the standard normal, and then we went, okay, what about real normal distributions when we're describing something like the heights of college students? And we're going to do the same thing here. So just like in that previous example, we have already done pieces of this. We just focused on how do we get from a percent to a z-score, or a probability to a z-score, or an area under a curve to a z-score. And now the only thing we really haven't done this before is we need to be able to go from a z-score to an actual value from the distribution. And we could, of course, use our z-score formula and then just use some algebra to solve for it, but I've actually done this for you on the formula sheet. On your formula sheet, which I've switched to that bright yellow sheet I handed out in class on Tuesday, you'll find two different formulas that are going to help us out with the normal distribution, and they are very helpfully labeled normal, so we know exactly where they are. So one is our direct formula. If you ever need to calculate a z-score, your z-score formula is there. And if you ever need to calculate a particular observation from a normal distribution when you have the z-score, I have the algebraically worked out version here. So we're going to do this on our question. That's how we get, from our z to an x is using that second formula, the inverse formula. But that being said, we're going to find a way to do this in the calculator as well. So I'm going to do one the long way, and then I'm going to do the rest of them and that one as well using the calculator instead. All right. So reading through our first question, we see birth weights are normally distributed. There's our sweet keyword to let us know we're doing something with our normal distribution. So we can either go to that normal section of the formula sheet or to the normal helps in the calculator. The mean weight of these births is 109 ounces with a standard deviation of 13 ounces. And we're going to answer the following questions using this information. All right, we see that a hospital puts any infant in the lightest 2% into the NICU. What is the cutoff for putting a baby in the NICU? We know that this is an inverse question because they've given us the percentage, which is the same thing as our probability and our area under the curve. So we could go ahead and draw our curve. Again, there are other ways to do this. We could say our x, I guess, is less, but to me, that's just annoying to use a probability notation. I like to just draw and visually see it instead. We know birth weights follow a normal distribution, so we got our curve. We know the mean of this normal distribution is 109, and we are interested in the lightest 2%. So we're going to start shading until we think we've shaded about 2% of the curve, so not very much of the curve at all. So this is my 2%. And we are looking to figure out what the heck this is, what that observation is, what that baby weight is. Before we do any math, we already know that that weight has to be something less than 109. So we're a lot further ahead than we would have been without doing this drawing. If we were doing this by hand, we would have two steps, just like we did in the previous direct questions. The first step would be to use this percentage, the 2% that we have, and turn that into a z-score. So we could do this. We could get our z-score by using inverse norm. And thankfully, 2% is a left side probability, so we can just use inverse norm with that 2%. We don't need to think about 1 minus or do anything fancy. I do need to put in 2% as 0.02 though. So I get out that my z-score here is negative 2.0537. So we have our z-score. The second step would then be, okay, now that we have the z-score, let's go find our x. And this is where we use our formula sheet and say, okay, I'm going to do an inverse question. I need the actual observation from the distribution we were talking about, so I'm going to use this formula. So going back, the formula is x is equal to z times our sigma plus our mean, or our mu. And this makes sense, right? Our z-score tells us how many standard deviations away from the mean something is. So all we're doing is saying, okay, let's put those standard deviations back on the mean, and that'll give us back where our original observation was. So if we do this, we have negative 2.0537, which, by the way, made sense because if you visualize the standard normal curve at 0 with 2%, this makes sense as it is less than 0. So doing the steps is actually nice because it gets us a way to check our work. We throw in our standard deviation and our mean, and then we just type all that in our calculator. So maybe a times 13 plus 109. Looks like we get out 82.3013 ounces. And if I didn't have a calculator that did inverse norm, I would just be sitting there doing the hunting in the middle of the table for 0.02 to figure out the z-score. And I would only be able to get out 2 decimal places for my z. Now, as we recall from the last video, inverse norm, it takes our left percent and then a mean and a standard deviation. So I don't have to just put in the mean and get a z-score. I could actually put in the entire question at once. I could have just done inverse norm of 0.02 with the mean and the standard deviation for baby weights. So if I do that, 0.02, with my mean and my standard deviation, I don't have to do any of the work there. It just pops out the answer right away for me. The only thing I need to do as a student is make sure I put my units back on there, because you guys know that I'm a stickler for units. So that's putting it all together. It's pretty straightforward, just takes a little bit of practice, and there are a ton of questions here for you to practice. Go ahead, pause the video, and try the next question on your own. All right, so coming back, we're still dealing with baby weights, which are normally distributed with a mean of 109. This time we're looking for the 95th percentile. So if you're in the 95th percentile on a test, that means you were better than 95% of people. So it is a percentile is a left side probability. Since it's the 95th, we need to shade past the mean, and this is a big fat baby. So we have that this area is 95%, and we want to figure out what that baby weighs. So chubby baby. If we're doing this in the calculator, inverse norm, it is a perfect setup, 0.95, 109, 13. Didn't have to do anything clever to think about, with our work here. You have to put it in as a decimal, 109 and 13. So we end up with 130.3831 ounces. So these are the only two that you have to watch. If you want to keep getting some examples, you want to see how this works when we're not dealing with something given to us as a left side probability, stick around. I'll just work through the rest of them, but I strongly recommend, if you are going to stick around, pause the video now and try these next 3 and then just double check that you got them right. The next question asks us about the heaviest 10%. So these are also fat chubby babies. So that 10% heaviest is a key word to tell me that I am shading on the right side of the table, or right side of the curve. So we really have to pay attention to keywords and what they mean, especially within a context of a question. Since we're here, we know we need to get a weight out that's bigger than 109. We can do our inverse norm. If you make a mistake here, you're going to see it right away, especially if you have the drawing. And this is why that drawing, again, is so vital. If we weren't paying attention and we did 0.1, comma, 109, comma, 13, right? We're going to get out a baby weight that's 92 ounces. Our drawing shows that we should have had a chubby baby, right? A baby over 109. So 92 is not going to cut this. This would just remind us that, oh crap, right? Our inverse norm only takes left side probabilities. And if 10% is on the right, that means 90% is on the left, because they're complements of one another. That's what needs to go into inverse norm. And drawing out the curve, make sure that we notice that and we don't do anything silly. So we should be doing 0.9, comma 109, comma 13. So I can bring back that previous one where I accidentally did the wrong side and just change that to 0.9. So we got this, 125.6602 ounces. All right, we could keep going. Next question we have is about a middle 80%. So now we want this 109 is still our mean. When we go to shade this, the middle percent is this thing, right? From the middle. So we're actually going to have two different baby weights. The baby weights are between. So if it's a normal baby, if it weighs between this and this. Otherwise, we need to be doing something. So this is where we have to think about, okay, 80% is here. That means 20% is left over in the tails, which means since it's symmetric, both tails must have 10% going on. So if we wanted to do the first, we'll call this x1 and x2. If we want to do the first x, we'll be doing inverse norm of 0.1, 109, 13. And x2 will be inverse norm of 0.9, 109. And 0.9 again, remember, just like the last time, because to the left of this bar, we have this 80% and this 10% for a total of 90%. 109, 13. So that's what we type into our calculator. And then for the last one, I'm not even going to do those. You've seen me type in inverse norm enough today. The last one, Q3. Q3 is our third quartile. It's been a while since we played with our box plots, but hopefully we still remember that. And we know something about the third quartile. It is the 75th percentile, right? If we drew out our whole little thing, 25, 25, right? 75th percentile. So Q3 is an evil way for me to test that you remember things about box plots and our measures from part 2 within this section. And it's essentially just another percentile. So it's actually given us a left side probability in a roundabout way. We know 75% of our data is to the left of that value. So if I wanted to find this particular baby weight, I could do inverse norm of 0.75 with that mean and standard deviation for our distribution. So that's it. That's using the normal distribution to find areas under the curve and to find cutoffs based on certain percentages or percentiles. It's pretty much everything we need to know. And that's what our worksheet will be on Thursday.